Welcome to the seminar Piping Flexibility Analysis and Piping Design from a Global Project Perspective, Problems and Problem Solving. Topics that will be presented in this seminar are part of a much wider course with the same title, and they are as follows. The role and importance of piping and pipelines in the industry. Possible causes of design errors and consequences which in some instances have been catastrophic. Addressing the root cause in piping design errors with particular attention to an interlink between piping engineering/design and stress analysis activities on a typical project. Bringing about the required appreciation of fundamental synergy. Benefits of computational analysis of stress in pipes and piping elements. It is well known that piping and pipelines play a significant role in the industry, but it would be good if we could somehow also quantify this. There are a number of sources elaborating on the topic, so let's see what one of them has to say. Around 25 to 35% of all material expenditure is spent on piping on a typical process plant. Also, 30 to 40% of all installation works. And finally, what is important for us to know in this seminar, 40 to 48% of all engineering effort is spent on piping. So we see that almost 50% of all engineering time is spent on piping. Another important fact indicating also the role and importance of piping can be seen through studies of root causes in plants' catastrophic failures. In 364 analyzed cases, technical engineering mistakes were contributing with 73%, out of which 25% have been related to piping. Below pie charts further show that within these 25%, design errors were participating with 26%, and they will be our main focus here. Now that we understand the importance of piping and therefore the requirement for adequate engineering effort, we will focus our attention on one of the little explored yet significant contributors to design errors. First of all, we have to understand the relationships between piping department and other design hubs on a typical project. As can be seen, piping department has to interrelate with other departments or parts of the project. Within piping department, two major groups are operating. One is piping engineering and the other plant design and layout group. Besides piping design and layout, piping engineering interfaces also with other groups as shown here, which are outside of the piping department. In some instances, piping design and layout is part of the piping engineering, and in that case, we can define the following piping engineering subfields: piping materials, piping design and layout, and piping flexibility analysis. The way piping flexibility analysis is used could directly influence the overall project results. So the best way to explain its importance would be with describing flexibility analysis through reactive and proactive design methodologies. In working with the reactive methodology, stress engineer is actually placed in the position of design verifier. Therefore, he will be verifying the designs that could be produced either by inexperienced designer or experienced designer. The design that will be produced by inexperienced piping designer usually comes for stress verification with insufficient flexibility. On the other hand, design that is produced by experienced piping designer would come for stress verification and will be too flexible. In both cases, stress engineer comes back with a request for layout rework, the difference being that the inexperienced designer would be given a request to produce new layout concept with more flexibility, whereas the experienced designer would be required usually to come back with a modified supporting configuration while keeping the same layout. In the end, either side will affect project results in a negative way, with inexperienced designer affecting the project through a slow process and long schedule, while experienced designer will affect the project through wasted space and excessive or wasted material. In proactive design methodology, piping flexibility analysis is recognized as an integral part of an engineering effort on a project and not just a quality control tool, which is typical for reactive methodology. So the efforts of two disciplines, piping design and layout and piping flexibility analysis, are combined at the early stages of the project, and designers are not left to single-handedly make important conceptual decisions without involving piping flexibility analysis. There is actually a bidirectional link between the two disciplines, with strong focus on integrity and communication, which are the main characteristics of this methodology, and this is typically becoming more and more important as project size increases. Because of this, regardless of whether the design is produced by an inexperienced or experienced designer, it is always going to be optimally flexible and there will be no rework required. As a result, projects are going to be completed on time and on budget. Now we will show the difference between two methodologies on the example of piping discipline document flow procedure. The following document flow procedure is the same for issuing work packs, isometrics, MTOs, or pipe support lists. In this reduced procedure, there are 31 steps in total. It is called reduced because IFR, or issued for review stage, is missing, as it was agreed with the client to optimize the process and make significant project savings by skipping the IFR stage and going straight from interdisciplinary check stage to IFU, issued for use stage. On the last slide of this segment, in the flow chart, we will see the continuation of the IDC stage of this procedure, but here we will now actually observe what is meant by the early involvement of flexibility and stress analysis on the project. We will follow this on the isometric and on pipe support list document flow procedure. The early involvement of flexibility analysis in development of both of these documents is scheduled to begin right after the step 1, or when ISOs, for example, are being prepared for IDC issue. On the next slide, we will now zoom in to see what is happening inside the box, which we call stress analysis and PS coding procedure. From step 3 of the document flow procedure for developing of GA drawings, which we are not going to discuss here in detail, basic information about the requirements for pipe supports are transferred to the designer who will be developing piping isometrics, which is step 1 of ISO's document flow procedure. During this step 1, there is a situation where a designer comes to a point that he must include the pipe support coding on the isometric. This is a specific code that contains all information about a particular support in a particular piping location. From this point onwards, there are two ways to proceed. One is shown with the green line and represents a conventional design process with reactive methodology, and there is a red line route that is marked as accelerated design process and part of proactive methodology. Conventional reactive design methodology that most are familiar with involves stress engineering review only after the isometrics are fully completed and with all pipe supports coding done. In accelerated proactive design methodology, before the isometrics are completed, at a very early stage of isometric development, the isometrics are sent to stress group for stress checking, and the pipe supporting requirements are fully determined and sealed from further change. Pipe support coding is done ISO is returned for finishing the design. Stress analysis can finish the report and issue it, and development of pipe support list can commence and can be completed at early stages. Strictly speaking, piping design is fully tied to flexibility analysis, and any change can only happen in synergy. In other words, any change to piping that is subject to flexibility analysis cannot be done without approval of stress engineering, and therefore the whole process is under strict control, and there is reduced possibility for errors that can be created due to lack of coordination. For example, the most common thing is when design makes a change to the supports believing it is minor, but is not aware that it may affect the flexibility analysis results. In the following slides, number 2, number 3, and number 4, we will look even deeper into the activity boxes within the stress analysis and pipe support coding procedure. As part of proactive design methodology, early stage isometric is developed and submitted for flexibility analysis. This isometric should contain enough information for the required modeling for piping flexibility and stress analysis. On slide number 3, we can see stress sketch isometric, which is created based on early stage isometric development. And on slide number 4, based on produced stress sketch ISO after performing piping flexibility and stress analysis, stress engineers define supporting needs and apply pipe support coding. This information is then used to produce a stress report, development of piping support list, PSL, and to submit to the design group for finalizing the isometric drawing. Here we can see the steps from 6 to 13, which are the continuation from the previous flowchart that was ending with step 5. And within those 13 steps, IDC stage of the document flow procedure is completed. Benefits of computational analysis are many, and in the realm of mechanical calculations of piping and pipelines, the following major types can be identified: static, flexibility, dynamic, remaining life estimation, optimization of piping designs using finite element analysis, forensic investigation and analysis. While this is important to know, often it is forgotten though that any computational analysis that is performed is generally trying to give answers in simple words to two major questions, and they are: how to do it to achieve the projected design life at the optimal design cost with maximum safety, and how to tell what went wrong in the design if premature failure occur, and once it is found, how to prevent it from happening again. Therefore, in the following slides, we will present on the first subject in the example number 1, flexibility analysis, and on the second, in example number 2, forensic investigation and analysis. In example number 1, we will show the piping flexibility analysis issues that were related to gas turbine cooling air system design. Gas turbine cooling air system consists of high pressure and low pressure systems, each one including its high pressure and low pressure coolers. Specifics of this analysis system was that coolers are positioned in vertical, suspended on spring hangers of the steel structure. So as the piping expands, it pushes the coolers, which move back and forth, so there is minimal restriction to pipe expansion and no need to have expansion joints in the system, except the one in the blow-off line. Also, there is no need for piping expansion loops, as the piping is flexible enough as is. All of this, together with steel structure, was analyzed as one system for most accurate results. The model is quite complex, so in order to enable easier modeling and analysis, it has been divided into smaller subsystems. The first one that we are looking at here is the high-pressure system with its OTC cooler. Second subsystem is the low-pressure system with the LP OTC cooler. The next subsystem is the anti-icing system. It is basically a line that is coming off the high-pressure system. In order to take the analysis altogether to another level of accuracy and comply with the most stringent reality check, high pressure and low pressure cooler steel structure subsystem was modeled and also added to the overall flexibility matrix. So the flexibility analysis model is assembled and therefore consists of the complete air piping and OTCs attached to steel structure via spring supports and snubbers. The analysis is then performed on it. On this slide, we see there were 7 different temperature cases that were analyzed, and temperature distribution for case number 4 is shown. Based on flexibility analysis, stresses were calculated and code compliance performed. Areas with the percentage of preset maximum values is displayed and analyzed. All this is done in order to verify the design through reactive design methodology. Benefits of computational analysis of stresses in pipes and piping components can be seen not only in design analysis but also in forensic investigations of failures. Actually, due to an incident on the previously analyzed and properly designed gas turbine air cooling system, where a weld seam at steam outlet failed, producing considerable damage, an investigation into the incident was carried out. The aim was to find possible design reasons for failure and generate necessary corrective design actions which will rectify the situation and produce a new solution ensuring future integrity of this type of piping designs. 3 parties were involved in the original design, which affected the location of failure: gas turbine air system design group, OTC vendor, and plant design group, and the failure occurred just below the interface line between plant and OTC vendor. So, theoretically, the failure point was in the jurisdiction of OTC vendor, but he has therefore, as a safeguard, defined the allowable load limits at the interface point, and plant has made sure with their analysis to fulfill these requirements. For the same reason, plant have also used appropriate displacement values from the gas turbine air cooling system analysis, which has been provided to them. It was found that regardless of the fact that everyone did their part properly, there was little cooperation in the reactive design methodology which everyone has followed, and that they all missed out on a very important fact, which is that dissimilar metal weld, when cannot be avoided in joining piping systems, create a somewhat peculiar situation where design for various reasons may result in producing joints weaker than expected and create a situation where failure due to fatigue may occur much sooner than expected. As a first step in rectifying the situation, a comprehensive model was created for conducting a comparative analysis. Instead of just using the displacements from the gas turbine air cooling system analysis, the analysis of the steam line was carried out on the model that contains complete OTC steam piping system as well as OTC cooling air system. The gas turbine cooling air system was included in the analysis to properly identify, evaluate, and integrate its impact on the steam piping system and bring more clarity to the investigation. Furthermore, in design analysis for the new solution, the method of analysis has combined stress results at the similar weld point from ASME B31.1 beam type Caesar 2 analysis with results from shell type elements FEM analysis. Existing Caesar 2 model of the complete cooling air piping OTCs with structure, spring supports and snubbers was completed with steam piping added. The aim was to compare the results of the existing steam piping analysis report with analysis based on a more detailed computer model once it became available. In conclusion to this comparative analysis, it could be said that nothing major was discovered which would have led to a decisive conclusion that a faulty piping design calculations were the cause of failure. In the investigation, nonetheless, it was noticed that if we look at the nozzle allowable load diagram, calculated piping loads on the nozzle were right on the allowable limit. Something else, however, much more important was noticed, and it was that a peculiar situation which is always present with dissimilar metal weld at the connection of HP steam pipe to the OTC was not addressed at all in the original calculation. During this analysis, firstly, the mapping of maximum shear stress distribution was carried out. It proved that with a simple positioning of the dissimilar metal weld to a location of the smallest stress, the design life would have been doubled. This finding was interesting also because it has shown that the existing location of the dissimilar metal weld was in the least favorable spot, at the location where the highest stress induced by external piping load has been occurring. The methodology of this design analysis has proved itself to be correct by calculating the expected lifetime to failure, which coincided very well with the actual time in which failure occurred. Failure occurred after 16,500 hours, and the corresponding calculated actual design life was 18,000 hours. Second most obvious observation is that if the dissimilar metal weld, instead of being right on where it was, if it was installed anywhere downstream from OTC steam outlet, the design life could have been significantly increased and perhaps even doubled if installed at the point of lowest maximum shear stress value. Based on everything revealed here, and as a first step towards new rectified solution, a practical, most advantageous spot for possible relocation of the dissimilar metal weld joint was selected as shown. Firstly, it is obvious that the location of dissimilar metal weld should have been discussed at the very early stage of the project. And finally, that it could only have been done if the proactive design methodology was in place instead of the reactive methodology, and this exactly was identified as the main reason that led to this catastrophic failure.